Welcome back, everybody. Today's lesson is on condensation, a little bit of clouds, and the dew point, and precipitation. So a lot of moisture today. All right, first, how does the water get up in the sky? Well, how does this water cycle kind of get this whole thing rolling? And we recall that the primary source of all this energy for weather is the sun. And of course, the sun is going to, when it comes up, cause a lot of water to enter the atmosphere by evaporation. Condensation of this water vapor back into a liquid returns it to the earth as precipitation. So that's how the moisture gets back here. Now we already know about condensation. We've studied this in the previous 2 weeks. It occurs when water vapor gives up some of its heat to the atmosphere. It releases 2,260 joules of energy per gram of heat in order to condense. That's right on the front cover of your reference tables. So that's quite a bit of heat that gets released to the atmosphere for that vapor to turn to a liquid. Condensation. All right, let's just fill in these little blanks here. Is when water vapor loses energy, changes phase into liquid water. And remember that magic temperature when air cools to that dew point, condensation occurs. Dew, clouds, and fog are all great examples of that. You can see some photos over there showing some dew forming on the spider web and the frost forming on the pine needles. Deposition occurs when water vapor transitions very quickly into a solid. So if it skips the liquid phase because the dew point's below freezing, we get literally water vapor changing directly to frost on a windshield, for example. And then the opposite of that, you notice the frost, sometimes it'll disappear, or a snowbank will just get smaller, and it's not because it actually warmed up quite a bit and melted it to liquid. It went straight to a gas, and that's called sublimation, kind of like what dry ice does. So these are some phase changes, and we're going to be spending more time in the next unit on phase changes, so I'm not going to get into it too much here. Clouds. Clouds are condensed water in the form of microscopic droplets. Now, many clouds are also ice crystals, microscopic ice crystals. But for now, let's just stick with this microscopic water idea here. And you can see some smog here in Beijing. Smog is a combination of smoke and fog, which that fog part of it is a cloud on the ground. And the Golden Gate Bridge, you can see sticking out of that fog bank there. San Francisco, famous for its morning fog. All right, 3 conditions necessary for a cloud to form. First, you have to have water vapor to have a cloud. So water vapor, it's, present in the air. Some places more than others. Second, the air temperature must drop to the dew point. So you must cool it down enough so it can start condensing. And third, and this is the part that maybe you haven't thought of, is you have to have something for that water vapor to actually condense onto. And there's a number of reasons for this. One of them is it absorbs a little bit of that energy, these little particles of dust, smoke, pollen, and sea spray. And as it gives up its heat, it instantly can condense on that surface. It's like a seed, if you want to think of it, for everything to grow onto. Well, a question that I often get asked, if clouds are condensed water vapor, if they're actually liquid, or even ice crystals, why don't they sink to the ground? And that's a great question to ask. A couple different answers to that question. One, remember that during the daytime, that air is being heated on the ground and air is rising. So we have these vertical currents going on, and those currents can help to keep those clouds aloft up in the air. And second, at any given time, there might be liquid droplets actually falling from a cloud, even when the day is sunny and there's clouds in the sky. But as it falls, it's evaporating before it hits the ground. And at the same time, there's rising air, which is forming new water droplets. So these droplets are just really, really, really tiny. Precipitation. All solid and liquid forms of water falling from the sky are precipitation. And of course, there's lots of examples. You've experienced them all. Rain, snow, sleet, freezing rain, hail, and drizzle. All good examples. Let's take a look at the formation of snow. And here we have a cloud. The snowflakes are falling from this cloud, and you can see the vertical temperature profile is pretty cold. So those snowflakes stay snowflakes all the way to the ground. Let's change things over to sleet and add a layer in the middle of everything that's a little bit warmer, above freezing. So you can see as the snowflakes fall through that middle layer, they actually melt into raindrops. But the bottom layer is very cold, and those raindrops freeze as little ice pellets we call sleet. Freezing rain, snowflakes fall, but that above freezing layer is quite a bit larger, and that raindrop that is formed from the melting snowflake hits the ground, and the ground is very cold, and when it hits the ground, it freezes on contact with the ground, and this is a really dangerous driving condition, freezing rain, probably the worst of everything. So that's freezing rain. It's, the raindrops hit the ground and then freeze. And then just plain old rain. Snowflakes fall, they melt, and the rain hits you in the head. Raindrop reality check, getting your perspective here. And you can see the typical raindrop, about 2 millimeters in diameter there, and how massive it is compared to everything else. And check out these typical cloud droplets, a large cloud droplet, normal cloud droplets. And then the microscopic condensation nuclei, those pieces of dust, dirt, pollen, sea spray, that those droplets form onto as little seeds. So raindrops are much larger, and that's why they fall, because they're heavy. Here's a common scenario, and actually I don't know who to thank for this. I pulled this off the net as it looks like it was kind of photocopied or something from a cartoon book, but it's good. So let's take a look at it. So first we have evaporation, sun changing water from liquid to a gas. And as that air, which is carrying the moisture in it, starts to rise, it cools off, at least in the troposphere, which is the layer we're concerned about, where weather is, the moisture is, and it cools off, and you can see the cooling represented by this surface temperature of 10, and then as the air rises, it's dropping and dropping, and that continues on until eventually that magic temperature. Now here you can see in this picture the temperature is 53, dew point's 51. We're not there yet. And as air rises and cools, it approaches the dew point temperature. And as you recall, the dew point is the temperature at which air is saturated and condensation can occur. Now we have equality here. Temperature is 51, dew point's 51, condensation starts to occur. And you can see the raindrops are real happy about that. Let's do it. Step 2, condensation. Changing the gas back to a liquid. As water vapor rises, it cools. When the air temperature is cool enough, vapor condenses into droplets. And don't forget those small condensation nuclei like dust and salt in the air. They're always needed. Clouds are made up of millions of tiny water droplets with dust specks inside. The darker the cloud, the more water it has. And it's not because of the pollution in the cloud. It's because it's getting thicker and thicker and blocking out sunlight from above it. That's why those really big storm clouds are so dark. And let's see, understanding the altitude of the cloud base. So on this right-hand side, we have temperature. I don't know if I can draw on this without messing things up. Nope, I can't draw on this. But we have temperature in the graph, and we have the dew point in the graph. And you notice they kind of slant towards each other because the temperature drops quicker as altitude increases than the dew point does. And you'll see relative humidity is that green line on the far right-hand side. And right now it's somewhere between 60 and 80. When it reaches 100%, that's when the cloud starts to form. So here we're going to play this, and you'll see a rising air, which will eventually reach that first dashed line, the condensation level, and watch what happens. So now we've reached the dew point. The air has risen enough to reach the dew point, and if we continue from this point, the cloud forms, and it grows in size. And relative humidity in that zone between those dashed lines is at 100%. And we're going to do a whole lab on this. If we haven't done it already, we're going to be doing a cloud-based altitude lab where you learn how to read these charts and actually plot your own cloud bases. Precipitation, the next step. Now the droplets are still too small to fall. Each one blows up and down, kind of swirling around in this cloud, combining with millions of other droplets, sticking together and getting larger. Finally, they become raindrops as they get large enough, and they stay too heavy to stay airborne. And so they fall as precipitation. So here's a good question you could be asked about this topic. Which graph best represents the relationship between water droplet size and precipitation? And the x-axis is droplet size, the y-axis is chance of precipitation, and it's pretty obvious that the bigger the droplets, the greater the chance. And so we have two rising axes there, and so the best graph would be choice 4. As droplet size increases, the chance of precipitation also increases. And there we go. So hopefully you learned a little bit about condensation and precipitation today, and maybe you'll experience some